Welcome to my talk about ESiWACE, the Center for Excellence in Simulation of Weather and Climate in Europe. And I'm going to tell you a bit about what ESiWACE does and how we contribute to the future of weather and climate simulations and what that means for the general public. So going back a bit in the past, here's a record of the last 800,000 years of, well, basically global climate. And at the top, you see carbon concentrations in the atmosphere, so CO2. And in the middle, you see tropical sea surface temperatures and Antarctic temperatures from proxy data. And at the bottom, you see a reconstruction of the global sea level in the last 800,000 years. And what you can see at first sight is that we have this periodic up and down, and the deeper past, it's all a bit more mangled in the records. But if you look at the last couple 100,000 years, we have these ramp ups of global carbon concentration, and then the slow decline again. And with those, you have ramp ups of temperatures in the tropics and in Antarctica, and also of global sea level. And so if you look at those last 20,000 years, you see that carbon concentration in the atmosphere rose by about 100 ppm, and with them the temperatures in the tropics and Antarctica rose, and also sea level rose by about 100 meters. So this is not the full last 20,000 years what we're seeing here, because of omitted the last 200-ish years. At the moment, we're at 412 ppm. So just within like 150, 200 years, we've gained more than 100 ppm in carbon concentration. And now this will not mean another 100 meters of sea level rise, simply because there's not enough ice left to melt to get the sea level rise, but it will mean sea level rise. And so looking into simulations for the future, here are simulations for the Max Planck Earth System model. So 100 simulations per scenario for the historical record. And then the so-called business as usual scenario with high carbon emissions. And then 2 different emission reduction scenarios, one more ambitious, kind of related to the Paris goals, one less ambitious. And this purple line here is just simulation where you increase carbon concentration by 1% per year. And that's a very good reference comparison scenario that we use for comparing climate models. And you see that not only temperature changes, but also precipitation. And with those 2, all other aspects of the global climate system. And so just looking at the ends here, with end of century temperature rises compared to, I think it's like 1960-ish, 1960 to 1990, somewhere up to 4 degrees almost. And then there's another degree that the historical record was colder. So we're talking like 4 to 5 degrees-ish of climate change, and that's really the same scale as the difference between an ice age and the present. Just that we're doing this in 100 years instead of like 10 to 20,000 at the end of an ice age. So we're going at an absolutely ridiculous pace here. And now we've recently had a report by the International Panel on Climate Change on what the difference between 1.5 and 2 degrees of climate change would mean. And I've marked their overviews here and put them into scale. So here's 0 degrees compared to pre-industrial. Here's like 1 degree. At the moment, we're in this 1.2-ish range. Here's 1.5, which was the aim of the Paris Agreement, 2 degrees, which is like the traditional best case scenario. And you really see that the corals, for example, are severely damaged at 1.5 degrees, and they're almost dead at 2 degrees. See that mangroves are severely affected, small scale, low latitude fisheries. So really the thing that the local people in all this tropical belt are living on. The Arctic is changing at an absolutely unprecedented rate. So changes there are super severe, and there's again much more damage if you go for a 2 degree world than for a 1.5 degree world. Same for a lot of other aspects. We had a few dry summers in the last years here in Germany, and the crop yields were severely reduced. And last but not least, there is heat-related morbidity and mortality. So people die and suffer from heat, and that affects thousands already in Europe every summer. So it's not like there's no change. It's really affecting us, and it will affect us more at 2 degrees than at 1.5. And it will affect us way more if we go deeper into this red territory, and that's where we're headed with the current climate politics. So if you look at what our governments are doing and what industry is doing, we're headed here. And it's usually called business as usual, but it isn't business as usual because there is no business as usual in a catastrophe. So it's more like apocalypse as usual. And now, assuming that we will have more climate change, that's guaranteed and will be somewhere, well, probably above this 1.5 line in the end. We really have to look at the things that are happening to us in this world. And for doing that, it's not the global temperature, but it's like weather. It's what's happening at your place at some day in the year. And here's 2 examples of that. One is a heat wave from 2019, the warm summer, where we had like temperatures in the 40-degree range in Europe. And there's tropical cyclones here photographed across America. So you have one in the Pacific, one making landfall here in the Atlantic, another one off the coast in the Atlantic, another one already coming up here. You have forest fires marked as red dots all over, especially here in the western US. You have the smoke of these forest fires blowing all across the continent. And these things are getting more and more severe. Everybody remembers the Australian fires. So for modeling these things, we really have to get high resolution, and we really have to get down to the small scale range, and that's what we're doing in ESiWACE. So here's a plot by Peter Duhm of ECMWF, so the European Center for Mid-Range Weather Forecasts. And it basically shows at what resolution scale you get what kind of weather and climate features, and it also shows what computer performance you need for that. And the typical like long-term prediction range currently is this 100 to 200 kilometer range, where you get the very broad weather systems, but you're not really able to resolve a tropical cyclone that's below 50, and especially if you want to have the deep convection that's driving these cyclones, where the air is rising up in the atmosphere, you have to get down to this kind of kilometer-ish range. And this is where we really want to go in ESiWACE. So we want to get these frontal gradients, we want to get deep convection, and if possible, at some point, shallow convection in the sub-kilometer range. But that needs computers with a peak performance in the exascale range. And that means our codes have to work on these exascale ranges. And so here's one example where we actually did this. So ECMWF got a grant for the American Supercomputer Summit, and they performed a 4-month integration with 1.4 kilometer grid spacing. And it's just an astonishing achievement in terms of resolution and in terms of making use of a big computer. Now, we're used to using big computers in weather and climate. We've been doing that for the last, I don't know how many years. So that's nothing new, but the scale is just getting bigger and bigger here. And we're getting to the point where we can do what we call the Polymer Turing test, where we compare model results to satellite data. And it's getting hard to spot the difference. So here's 10 times a model result from a model intercomparison that we call Diamoon, where we call for kilometer scale models to give us their data. And as ESiWACE, we support the whole thing with hackathons and with disk space and support around it. And so all this data is collected here at DKRZ. And Nicholas, my colleague, has made this beautiful visualization. And it's really hard to tell which one is the satellite. And so 3 of these are ESiWACE simulations. One is the satellite, and the others are simulations by other teams. And this is the satellite image, and one of my colleagues says he can tell it because there's a bit more algae and stuff in the water around Australia. But you really need to know what's going on and what to look for if you want to have any chance at telling those things apart. And that also means we're getting to these processes that are really happening there, and we're really getting them. And so now I'm going to do a bit more of the project view. What are we doing in ESiWACE? So we have the 7 work packages, and work package 1 really does the production runs. So they work on getting the models on the computer, seeing what happens, optimizing things. And one aspect here is Silk as a workflow engine that we support in ESiWACE, and people can actually apply for support with Silk, and they can get free support here. So please check our webpage if you need that. And once we've run the model, or once the model is running, we get ridiculous amounts of data. So I currently have about a petabyte of data on disk that I have to care for from this diamond in the comparison. And we're developing tools for that with the ESDM software middleware for storing data. And you don't only want to store it, you also want to look at the data. So here's Catalyst and ParaView as 3D visualization software that can even be fed directly from the model without even having to go to disk. And we have a FIDIA, which works on these data cubes and just does massively parallel analysis of data. So you get your diagrams, maps, charts, tables, all this for getting to the insight that we want to have at the end. Now, we also have the new computers coming up, and with new hardware, we need new ways of programming. That's where the domain-specific languages come in. So we have Cyclone and Grid Tools as the two European domain-specific languages in weather and climate. And we support those two for modernizing model code. And we also support containerization, so you can run it on the supercomputers more easily. And we don't only do all this work for ESiWACE itself, we also have a service team that helps other groups in weather and climate. So again, you can apply here for free support for getting a more parallel, better code. And those teams that have used this support were very happy with it. So please check our webpage, please apply. We're very happy to help you. And we also have an outreach team that runs a summer school. So we'll have another summer school on high performance computing in weather and climate this fall. So please check our page, please go there. We run a whole bunch of smaller courses. Again, please check them. And as another service, we have XIOS, which is an I/O server that gets data from the model to disk in an asynchronous way with parallel I/O. And the same does CDI-PO, which is developed at DKRZ. So we have this whole chain, and of course we have one more work package for the management. And I'll briefly go through these work packages in a bit more detail after I've covered the project partners. So here on the left, we have these teams that are really in this climate research field. We have weather services, we have people that provide tools, and we have the supercomputing centers, as well as the industry. So we have all the different teams working together on this one issue. And I mean, that's the strength of these European projects, that they can actually bring everybody together at a table. So work package one really does these simulations. So they do the high resolution simulations, and we're doing the diamond intercomparison, where we bring together all the data from different teams, so we can compare what's going on in which model, what is common to the models, what is different between models. And we do these scalability experiments up to this thing on Summit, where they did 112 simulated days per day at 1.4 kilometers with IFS. And that's just an astonishing achievement, getting to this resolution, which was totally impossible a while ago. We have NEMO scaling up to about half a simulated year per day on the Mare Nostrum 4 supercomputer. And ICANN is a member of the HiDALGO team. for scaling up to 500,000 blue gene cores. So we're really in this range where we can use the biggest supercomputers, and we will also need the biggest supercomputers to do these simulations. We still are constantly looking for new things coming up on the horizon. So we're doing this whole work on the domain-specific languages. We're looking into more concurrency in the components to scale better. We're doing the containers for getting the models onto the new hardware and for having a more consistent environment on a supercomputer. And we're doing all this, looking into new emergent technologies like machine learning. And all the knowledge we have, we really try to bring it out into the community. So we have these service calls for different aspects, and we have the HPCW benchmarks, where we provide a benchmark that is a subset of the weather and climate model, but it will give you, as a hardware vendor, it will give you a chance to optimize your computer for our needs. And they were developed by the ESCAPE 2 project, and we will take them over soonish. And there's a whole bunch of supercomputers that are dedicated to weather and climate. So there really is a market for these things. And this benchmark just makes it easier for vendors to produce for this market. We have trainings, and we do these service calls. So please check our webpage. Please have a look at the training program and the service calls. We're very happy to help you here. We have the whole storage thing, how to get data stored on different systems, how to access it faster. And we have visualization. So if you just look at this image of Earth in a simulation, if you take a 5-kilometer resolution simulation, which isn't the highest resolution you're running, but you still already have 8,000 grid points across the equator. So if you want to just view every grid point as a pixel, you'd need like an 8K screen or 4K screens just to see everything that's going on in the model at once. And for the higher resolutions, the numbers would get even more ridiculous, and you need big computers and good algorithms to actually look at these things without waiting forever for your image or just having your computer die out of memory. So we're really working on these things. We're doing all the schools, all the trainings. We're, of course, interacting with the whole HPC ecosystem. So with the task force, with PRAISE, we're doing workshops. Check our webpage, go visit. And we're not just doing this on our own, of course. We're part of this whole European ecosystem of infrastructure, of new technologies coming up, and of the applications. And we're somewhere in this application range as one of those funded centers of excellence. And just looking at the weather and climate landscape, we are one of many projects on the European level that are really working on getting climate and weather simulations up to speed. And the biggest one that's now coming up is Destiny, where things are about building a digital twin of Earth and going all the way from the high resolution modeling and from satellites all the way through the systems to policy decision making. So giving people a chance to really decide how they will locally act based on weather and climate forecasts. And I just want to end with this animation of 3 simulations that we did here at DKRZ together with Max Planck and the German Weather Service, where we ran the ICON model one time at 2.5 kilometer resolution, just the atmosphere with a numerical weather prediction toolkit. And then at 5 kilometers with the climate physics toolkit, and at 5 kilometers with atmosphere and ocean coupled. And while I made the animation to point out the differences between runs, you really see that they share a lot of commonality. And you can really see these weather systems here forming and going around Earth, doing their thing. And you can see the diurnal cycle coming from east to west as the sun rises in the east and then it just moves across Earth. So there's so much to be seen and to be found in these simulations, and it's going to be really challenging just to exploit what's there once we have them. And with this, I would like to end my talk and thank you for your attention.